Hi, in this video, I'll be talking more about the real numbers, and in today's video, we'll be going through what are intervals and what is the nested interval property of the real numbers. And this will end off with giving you a proof of why the real numbers is uncountable using its properties instead of what Cantor suggested in his diagonalization. So let's continue. So we first note that we define an open interval as the set where x is in between a to b, and we denoted it by this bracket a comma b. In this case, the endpoints are not included in the interval, so x cannot equals to a or x cannot equals to b. And if both endpoints are included, so x is less than or equals to b and more than or equals to a, then we use a square bracket to denote it to be a closed interval. Then of course, with that you have half open, half closed, and you see that this works for infinite intervals as well. And for infinite intervals, because infinity is just symbols, they are not elements in a real number, so it's always an open bracket towards infinity. So this is the definition of an interval, but it's quite hard to use it because you won't be able to always tell whether your set is an interval. So there is this property that we want to give to an interval so that we can prove whether the set is an interval. So the property is that if there are any 2 points in the interval, so you can imagine the line as this, and then your interval is from a to b. If there's any 2 point x and y inside it where x is less than y, then the closed interval will be a subset of the larger interval S. And if this occurs for every point, then S is an interval. And so there are 4 cases to consider when you want to prove it. S is bounded. S is only bounded from above. S is only bounded from below, or S is unbounded. If S is bounded, then we can let A be the infimum of S and B be the supremum of S. Thus, it's clear that S will be a subset of the closed interval A to B. What we want to show now that A comma B, the open interval A comma B, will be a subset of S as well. And so for any Z in between A to B, Z will not be a lower bound by definition. And so there will exist an X inside S such that X is less than Z. Also, Z is not an upper bound, which means there exists a Y greater than Z. And therefore, Z lies in between the closed interval X to Y. And so this implies that Z is an element of S. Since Z is an arbitrary element of A comma B, we can conclude that the open interval is contained inside the interval S, or soon to be proven to be interval S. And with that, we just need to check whether A and B are inside or not. So if A and B are inside, then S will just have to equals to this, because it's already containing the open interval and is contained within the closed interval. And you can check that for the different cases whether A and B are inside or not, then it will lead to the possible different types of intervals. So in any scenario, it will always be an interval. And for the other cases, it's proved similarly, because if it's bounded above, then there's a supremum. If it's bounded below, then you have an infimum, and the other part goes to infinity. So in either cases, you always have an interval. So you can just check that and it will be left as exercise. So what we want to characterize now is something known as a nested interval. So now that we know what is an interval and how we want to characterize them, a nested interval is just a sequence of inclusions. So the first interval will be the largest. So we can see this diagram to have a better overview. So a sequence of intervals is known as nested if the first interval is the largest, it contains the second interval, and it contains the third and fourth. And so every intervals get smaller basically. So the n+1 interval is contained within the nth interval. So if you can see that if the interval is the closed interval 0 to 1 over n, then this is a nested interval sequence and the intersection is equals to 0. However, if it was the open interval, then we see that there is no common point, since given an x, there will exist an m such that 1 over m is less than x. So x is not within the interval m. And this results in the sequence having an intersection with no common point. But what we shall prove now is that in a sequence in real numbers, every nested sequence of closed and bounded intervals will have a common point, like over here. And so, how do we prove such a property? Well, it relies on the properties of the real number. And so, if you are given a sequence of closed intervals, which is nested, then you must show that there exists a common point there exists a point in the real numbers such as the point lies in all the intervals. So since we know the intervals are nested, we know n is a subset of the first interval. And so for all n, an will be less than or equals to b1. So you can see it over here. So the an terms will always be less than the bn's, and all the b's are less than b1. So it's the set of an's are bounded above. And so we just let epsilon be the supremum. But we shall then now show that this supremum is actually less than all the bn's. And this is quite clear because the bn's are upper bound of the an's. And so, in any scenario, because epsilon is the least upper bound, epsilon will be less than or equals to bn for all n. And this concludes that epsilon will be in between an to bn for all n. And hence, epsilon is an element of the interval of all the intervals. And so the proof is quite simple, and I hope you have followed through. And this really is relying on the fact that there is a supremum in the real numbers. And so you could say that the real numbers can be characterized with the nested interval property as well. So one more thing to take note is that if you're given a nested sequence of closed and bounded interval, then and the length of the interval satisfy that the infimum equals to 0 as n goes to infinity, of course, or like n runs through all natural numbers, then the epsilon here is unique. And so the same argument follows, but now you just need to show the n which equals to the infimum of bm equals to the supremum of an. And so I'll leave the proof for your reading, but it should be fairly simple to follow through, because it's similar to proving the nested interval property, but instead of using an as the set where you use the supremum, you use bn as the infimum set. And really, with this property now, it gives us a proof that relies on the properties of the real number to show why it's uncountable. And so we just need to take the unique intervals 0 to 1 and we assume that it's countable. So we can enumerate through x1 to xn and so on. Then we define a closed interval I1 such that x1 is not an element of I1. So it contains like some elements from here. And then we select another closed subinterval such that x2 is not an element of I2, so some elements in here. And so on. So you obtain a chain of inclusions. And because of that, by the nested interval property, there will exist a point such that epsilon is inside all these INs. But that is not possible because the epsilon cannot equals to any of the xn's, and that is an enumeration of the whole I, and hence I is uncountable. And because I is uncountable, this shows that the real numbers which contains I is also uncountable. And hence we have proven that the real numbers is uncountable using a different proof from Cantor's argument. I hope you have enjoyed this video and I've come to the end of it. I'll see you in the next one. Bye.